Hello everyone, welcome to Vocabulary of Physics, in which we are going to discuss concept of force here. It's a very important fundamental concept. Let's get into it. First of all, the basic definition of force: push or a pull. This comes probably in 7th grade and 8th grade. To understand it a little more in depth, let's understand the concept of equilibrium. When a body is experiencing two or more forces, and if these forces balance each other, we say that the body is in equilibrium. And equilibrium are two types. One is the static equilibrium where the body is at rest. The other one is the dynamic equilibrium where the body is in motion and yet the forces are being balanced. As far as static equilibrium is concerned, we know it since antiquity, whereas this dynamic equilibrium is relatively a new concept that we understood. Let's get into the way the concept of force has been evolved over the centuries. So initially during probably Aristotelian era and before that, it was assumed that force was needed to keep the body in moving motion. So even to move the body, you require a force. That was the idea. But during that time, the concept of friction has not been developed much. That's why even to move the body, you require a force. That kind of a fallacy we had. This is not correct. Later on, it has been rectified. So by the time you come to 17th century, probably around 2000 years later, by that time concept of friction has been understood. You can change the friction of a surface there by smoothing it and otherwise applying lubricants. Conceptually, if you are able to make the friction zero, then you can move the body forever without applying force. So force is not needed to keep the body in uniform motion. Only to change the velocity you require force. This is called dynamic equilibrium. Then comes Newton, and he gave a very comprehensive, elaborated definition of force through his laws of motion. Then relativity, Einstein theory of relativity comes and says that force is, this gravitational force is not force. In fact, it is a result of curvature, warping of space and time there. And after that, when we go to subatomic level, where we need to use quantum mechanics, there is no concept of velocity, acceleration, displacement at quantum mechanic level because everything is probabilistic there. So there, the idea of this force itself becomes very redundant there. That's the point there. So now let us give a definition, formal definition for force. Newton's first law gives the qualitative definition of the force. Force is a physical quantity meaning which can be measured, that can change the state of motion of an object. Imagine a person going in a gravity-free space. So the person who is going, he'll continue to go in the same direction with the same velocity unless some external force acts on it. So external force is needed to change the motion, but not to maintain the motion. That is one idea. But now when we go to quantitative definition of force, that is given by Newton's second law, the net force acting on an object is equal to the rate of change of its linear momentum. The net force, sigma meaning summation of all the forces acting, is d by dt meaning rate of change of linear momentum, where p is linear momentum. So this is a quantitative definition we have here. Then comes Newton's third law, where it talks about the source of force. So the force is generated or induced because of the interaction between two objects. So whenever two objects come and interact, the forces will also be in pairs. A exerts force on B and in turn B exerts force on A. So the forces will appear in pairs. Example, you consider rocket propulsion there. So the gas which is being pushed down because of the excess pressure that is created inside the combustion chamber. So the gas is being pushed down. That's action if you will consider. In turn, the gas will push the rocket upwards. That is the reaction there. So that's what you have. But anyway, when you are defining force, you need to remember that Newton's laws are valid only in inertial frame. So this definition assumes that the frame of reference is inertial. So the concept of inertial frame, I am going to discuss much in detail in another video. But for the timing, let's move on further. Now, how do we add, subtract forces? So force is a funny thing because it is involving with the direction also. If I apply 4 Newton and then 3 Newtons, 4 and 3, when you add them together, it need not be 7 Newton. It can be 1 Newton also. It can be 5 Newton also. It depends on the direction between them, angle between them as well. So force is a vector quantity which has got both magnitude as well as direction. Algebra vectors is something different from what we do in real number algebra. So to understand that, we call this as parallelogram law. Imagine a ship which is being pulled by 2 boats. boat 1 exerts force F1, boat 2 exerts force F2. The resultant force, that is Fn, can be identified by using a construction of the parallelogram with these two forces being the adjacent sides, and the diagonal which is passing through the common tail of these arrows represents the net force. So the ship would actually move neither in F1 direction nor in F2 direction, rather it will travel along the diagonal lines. That's a net force. So this diagonal will represent both in magnitude as well as in direction as the resultant of these two forces. This is called parallelogram law of vector addition. So this is the way we combine forces. Sometimes we might want to split the forces also. Splitting of forces is called resolving of forces. So resolving can be done mathematically by using trigonometry. Imagine this is a force you have, you drop a perpendicular. The influence of this force on x-axis, otherwise shadow of the force on x-axis, we call it as f of x, and similarly onto y-axis f of y. F of x and f of y can be calculated using trigonometry, using cos theta, sin theta. So we'll discuss that as we go on. This is splitting of the force there. Now that force is a very important concept, so there is many ways that you can classify the forces. Let's look at one certain cases of how we can define forces into various classifications. Number one, contact and non-contact forces. In some cases, you require contact for the force to be experienced. Tension, there is a contact between the string and the body, normal reaction there. There's a contact between the table and the block, friction, contact force. Similarly, you can have non-contact forces. Even without any contact between Earth and Moon, there is a force between them. This is called field force or force at a distance. Positive charges repel each other. This is electrostatic force. Here you have magnetic forces. These are all forces without contact you can have. These are called non-contact forces. And then we have another category. It depends on the amount of heat that they may produce. So whenever a force performs work, and consequently the heat is produced, then we say that it is a dissipative force. The other one is a non-dissipative force where heat cannot be produced. So it can convert mechanical energy into thermal energy. A dissipative force is the one which can convert from mechanical to thermal. Examples: kinetic friction, viscous force, and collision forces, especially during inelastic collision, where you have a permanent deformation and also heat being produced there. When you go to non-dissipative forces, where the heat cannot be produced, mechanical energy cannot be converted into other forms of energy. Maybe potential to kinetic is fine, but other way also okay, but total mechanical energy seems to be conserved, or it cannot be converted into thermal energy when you are having non-dissipative forces. Example: gravitation, spring force, electric force, magnetic force, and elastic collision forces, which is an ideal model. Elastic collisions you would generally not see in daily life, but billiard ball collisions probably can be taken as approximately elastic collision. Okay. Next, another classification is depending on the nature of the work. Imagine that a body is moving from A to B. You can either take it from path 1, or otherwise through path 2, or you might have many other paths as well. You can have infinite number of paths between 2 points. If work done by the force is independent of the path chosen, then we say that force is conservative force. Example: all these field forces and also spring force. And non-conservative forces, different paths perform different work, then we say they are non-conservative forces. Mathematically, dealing with conservative forces is much easier than non-conservative forces. So in the future videos, we'll discuss a little more about these conservative forces when we study about potential energy. So that's one categorization. Next one is impulsive and non-impulsive force, especially when you are dealing with collisions where the huge amount of force acts for a very short duration. Such forces are called impulsive forces. Non-impulsive forces are finite forces which act for a long duration. For example, gravitational force has been acting on you even before you are born, and they will be acting even after the person is dead. So as long as the mass is present, there is a gravitational force. It acts for a long duration, but it is not very large. It's finite quantity. Gravitational force, spring force, these are the examples for non-impulsive forces there. And then we have another categorization based on the direction of the force. Imagine aeroplane is going in this particular path. At this point, if I draw a tangent, this is a tangent. Perpendicular to that, you have normal here. The net force that is acting on the aeroplane can be resolved into components: tangential component and normal component. The tangential component is called tangential force, and normal component is called normal force. The force which is tangential to the path is called tangential force, and the force that is normal to the path is called normal force. And normal forces are also called centripetal force. This is another name because they are directed towards the center of curvature of the path. Centripetal, center seeking forces. They cannot change the magnitude of velocity, they will only change the direction of motion. Whereas tangential forces will be, they are always tangential to the path, they can change the speed, but not the direction of motion. So these tangential and normal forces will be studying separately in a very much in detail, but just a classification I am looking at here. Next comes internal and external forces. You have a system. Within the system, if the objects are interacting with each other, that they are called internal forces. But from the surrounding, if some force is exerted on the system, we call it as external force here. So it depends on the system. The forces that act between the parts of the object in focus are called internal forces. Example, internal muscular forces of a person, otherwise tension in a string or a spring. And what about external forces which act from the surrounding? So the forces that act on the body by the external agent are called external forces. And Newton's law only talks about external forces. Newton's law cannot accommodate internal forces. Internal forces cancel out, balance out. Only external forces can accelerate the center of mass of the system there. Then comes the fundamental classification. Whatever we have seen so far, they are only macroscopic level. Microscopically, if you go and try to understand the reason, the source of these forces, all the forces that we observe can be categorized into four baskets. There are four baskets that you have. Two baskets will correspond to long range forces, where the force can extend far off distances, and the cases are gravitational force and electromagnetic forces. The other category is short range forces, where they are confined only for a certain region within the nucleus, strong nuclear forces and weak nuclear forces. They are very strong, but they have a very small range as well. Only within that range they will be appearing, but at macro scale you cannot see them. And these are the only forces in the entire observable world. So fundamentally, any force that you observe has to fall into these two categories only. There is no other category apart from this force. For example, friction is electromagnetic force. Normal reaction, electromagnetic force. Tension, all that is also electromagnetic force. There is one statement that you need to remember. In daily life, that means at macro scale, we encounter only two kinds of fundamental forces, either gravitational force or electromagnetic forces. So in daily life, except gravity, whatever you observe, they are fundamentally electromagnetic, like friction, normal reaction, tension, all these are electromagnetic in nature. Now let's look at gravitational force. This is one of the most fundamental forces, very easy to understand it because it's common there. It is everybody's intuition about, but then it is also very controversial force because as you study it deeper and deeper, it becomes really elusive. So initially, when during Galileo, he has proved that irrespective of the mass, every object falls down onto the surface of the earth with nearly same acceleration, 9.8 meter per second square. And then comes Newton's law of gravitation. So before Newton, there is a perception that the earthly objects follow certain rules and the heavenly objects have a godly rules. So they are not going to be mixed up like that. But Newton said whether it is a celestial object or the earthly object, all of them should follow the same laws, laws of motion and laws of gravity. And that way he was able to unify everything together. Einstein's relativity comes later and it says that first of all, force is not, gravity is not a force, first of all. And it says that this gravitation is because of space-time warping. So that is a very interesting phenomenon. And then comes quantum mechanics. Quantum mechanics is trying to include this gravitational effect in whatever theory that we have here. So, but it is not being successful so far, yet to accommodate gravity in whatever standard model that we have to understand quantum mechanics there. So electromagnetic force is also one important fundamental force. This is the one it talks about quantization of charges. So quantization has been known to us already well before quantum mechanics through charge quantization. Anyway, starting with Coulomb's law and Gauss law, they talk about electric forces, especially when the charges are at rest. Whenever the charges move, they also produce electric force as well as magnetic force. To understand magnetic fields, we need to study Biot-Savart law. Then comes Faraday's law. Whenever a magnetic field changes with time, you see that electric field is created. And then comes Maxwell. He questions very important statement. If unsteady magnetic field can produce electric field, why can't the other way around be possible? Like when you don't, why can't you have unsteady electric field producing magnetic field? With that idea, he has collated all the electromagnetic equations, 20 equations, clubbed them together, and he formulated a new theory called electromagnetic wave theory. So that is very important, groundbreaking theory that we have here. Then comes strong and weak nuclear forces. They are considered, they are observed only within the nucleus. These strong nuclear forces are basically spillover effects of gluon exchange within the proton or neutron. So these forces are responsible for holding the protons together or neutrons together inside the nucleus. But of course, these strong nuclear forces are very short range. We don't know why they are very short range, but it is happening. It is observed to be very short range that we have. Then comes weak nuclear forces. They are also very short range. They are basically responsible for beta decay or something like that. And they have been proposed that due to exchange of bosons, these forces are being created. And later, it has been observed that at a very high temperature, this electric force and this weak nuclear force can be combined together into a single entity. We call it as electroweak force theory. So next, let us understand the cause of force. What are the various causes of force? This is also important for us. The first thing is when you apply force, an object can change its speed. If speed is changed, obviously kinetic energy can be changed. But sometimes it may not change the speed, but it can also change the direction of motion, especially when the force is applied perpendicular to velocity. Like hitting a ball with a bat changes the direction of motion. And also it can change the rotational velocity, not just the linear motion. Something is rotating, let's say you can slow it down or speed it up depending on how you are applying force. That we call it as torque. Then we have change of potential energy. Suppose I lift the object upwards. So I'm doing work on it, thereby I'm increasing the gravitational potential energy of it. So you can perform work on a particular body using a force, and thereby potential energy can be changed. Of course, performing a work, that is one aspect. Change of the shape. If you have a deformable body and you compress it, twist it, and otherwise stretch it, so you can change the shape of it. Like you take a spring and stretch it, compress it, or you take any object and twist it. So the shape of the body can also be changed. We call it as deformation. And then you can also break the object. These are the general effects of force. These are mechanical effects. And based on whatever effects we are considering, there are some definitions which come from force. Based on force, these definitions have been derived. Number one, rate of change of force. You call it as yonk. And then double rate of change of force. Okay, that is called tug. And then triple rate also you can have. We call it as snatch. Of course, they are not very famous, but you can define them. Differentiating force, first, second, third order, we can have. So instead of differentiating, you can go for integration. If you integrate with respect to time, you get impulse. And if you integrate it with respect to position, you get work done. And if you differentiate work with respect to time, you get power, rate of work done, which is also equal to F bar dot V bar, force times velocity, dot product, of course. And then torque, R bar cross F bar, which is related to rotational effect. Then we have potential energy minus integral F bar dot dr bar. Of course, this is defined only for conservative forces, and here we don't put any limits, meaning it is indefinite integration. Then we'll conclude here with the final certain words that we have used so far. So these are the words that I have used here. You try to understand them with the concepts of physics here. So with that, I'll conclude. Thank you very much for joining us. I hope you understood. Until next time, goodbye.